Hello everyone, this is the video for section 11.3, looking at error and precision in measurements. Uh, yeah, this is going to be a short one, so let's just get through it. You don't really need 11.1 or 11.2 to do this, to be totally honest. So yeah, this is pretty independent of everything, but still important. There's still some important stuff here, so I don't know, why not? Let's just get started. All right. So imagine somebody asks how old you are. I mean, what kind of answer would you give? You're probably not going to give an answer down to the day, the hour, the minute, the second. At the beep, I'll be exactly, however old. You just give them a year, and that's what most people do. Now, the question is, how accurate really is that answer? You're introducing a certain amount of error in your answer. I'm closer to my next birthday at the time I'm recording this, but I would give my age of the birthday that I've passed. And so I'm actually closer to the next birthday than the one that's passed. So I'm actually introducing a lot of error there. It's not a very fair representation. You get to a certain age, you're more inclined to give the smaller number anyway. But unless you just had a birthday or you have a birthday coming up in the next few days or weeks or in the next month or something, you're probably not going to mention that. You just drop it down to the last birthday that you've passed. So in this section, we're just going to talk about how things are inaccurate, how we use inaccurate things, and then what that does to the work that we do. So there's two terms that we do need to define in this section, and that's the theoretical measurement and the actual measurement. So in the previous example with my age, the theoretical measurement would be just the number of years that I would claim to be and just say as my age. It's the measurement that we use. It's a little weird to talk about this as theoretical because it is my age, but I guess calling it the inaccurate measurement doesn't really work. So it's the measurement that I take it to be, that I assume it to be. It's my age sort of in theory. So even though that theory is based on some degree of fact, the accurate measurement is what we would call our actual measurement. So it's what it really is, and any difference between that theoretical measurement and that actual measurement create a certain amount of error. But if you think about it, we do this all the time. I mean, it's just a thing that we do sort of informally or colloquially or idiomatically or however you want to think about it. We just don't always say things with the utmost precision. And in fact, sometimes when people do, it seems kind of awkward. The example there, if it was 11:58 and you said, it's noon, I'm going to have some lunch, and somebody said it's actually 11:58, you just kind of look at them like there's no point in that. Even though they're being accurate, I mean, they're using an actual measurement. It just seems like a real sort of like pedantic thing to do. And then, really, if we want to get into it, we could even get into whether or not that's an actual measurement because that's being rounded to the nearest minute. We're not giving the time to the actual second or even decimal of a second. So there's always a certain amount of error in things, but we just want to try to keep it as minimized as possible. The problem with error is that once we introduce it into something, the more we use things that have that error, the worse it's going to get. It starts to compound, and so the more we use incorrect measurements, or just the worse they're going to be. If we're building something and we don't measure the pieces of wood, for example, that we're using to build, say, a house, it may not make that big of a difference for that one specific piece of wood, but as the house continues to build, all these little bits of error, we like to think they cancel out. They don't. They just sort of keep adding up and adding up and adding up until eventually, we've got a wobbly, lopsided house. And that's what happens in mathematics. The more we introduce these errors into our calculations, the more work we do with that error, the worse it gets. So this sounds a little contradictory because I'm saying now that a certain amount of error is bad, but I said in the previous slide that a certain amount of error is pretty much always going to be there. So how do we know how precise we need to be? How precise is enough? How much is, too little? How much is too much? How precise should we be? For the most part, the work you're going to be doing with, K through 6 students, the level of precision isn't, hugely important. You don't want students to do crazy things like round 51 up to 100, because now the amount of error is almost equivalent to the actual number that you're trying to measure. So, for the most of the work that you're going to be doing, the eyeball test is going to be pretty sufficient. If the answer that the student's giving looks really far off of where they're supposed to be or what they've meant to have measured, then something's wrong. Sometimes they just grabbed the wrong unit. Sometimes they've read the ruler wrong, and sometimes it is due to just rounding something or estimating something. Um, to the degree that there's just way too much error, and then you need to kind of ask them to, be a little bit more precise. As a general rule, though, when you're doing a math problem, you want to look at the way the numbers are presented to you, and you want to give an answer that's as close to those numbers as possible. Um, if the problem's in meters, you typically want to give the answer in meters, unless the problem says to do otherwise. I mean, obviously, if the problem says convert this number of meters into centimeters or kilometers, then you're going to change the units. But if it doesn't say to do that, typically meter stays in meters. Maybe more to the point of this section, uh, typically the number of decimal places is going to remain consistent. So if a problem is given to you, like in this example here, 3.2 divided by 1.4, well, the numbers that we've been given are to one decimal place. And so if we divide it out on a calculator, we get, this continuing decimal. So we just look at the numbers that were given. They were one decimal place. One decimal place is probably more than enough. In certain classes, in certain science classes, you may hear about significant digits and other ways and structures for doing it. But for the work that we're going to be doing and the work you're going to be doing working with students of this age, this is a good standard to work by. It's not by any means universal. This is not the only way to do it. Some people would probably argue against doing it this way, but for the work we're going to be doing, it's going to be more than sufficient. For the checkpoint problem, man, I got nothing. Yeah, there's not really a problem I can come up with. I mean, I suppose if you feel like you need to do something, think about other ways in which you introduce error into the problems that you do, or something like that, or do a problem like on the previous slide where you're dividing and then making sure you do it to the right number of decimal places. But I mean, for the most part, that's it. Just understand the difference between theoretical and actual measurement. Be aware of the error that you're introducing into problems. Um, Man, that's about it. So I don't know what questions you might have on this section, but if you have any, bring them to class, and as always, we will get them answered. All right, thanks.